for good morning, good evening. Thank you for inviting me to speak here, and thank you everybody for coming to my lectures. So what I plan to do is give this, so it's going to be a condensed version of my semester-long graduate course on induced subgraphs. I'll do less details, less proofs, and obviously I'll have to skip some topics, but I think in 4 hours I can cover at least all my favorite parts. This is sort of, this is a great way to teach, right? I don't have time to do everything, so I really can choose and teach you only the things I really like to talk about. So that's what it's going to be. It's going to be my 4 favorite lectures. And let me just say it again. So if you have an urgent question, please just unmute yourself and ask. If it gets too unruly, we'll do something else. But for now, I think this is best. And then if you have a question that can wait to the end, then let's wait to the end, and I can, I'm happy to stay for a few minutes at the end and talk to people about the questions they may have. All right, so this is my whiteboard. This is where my life has been taking place for the last year and a bit. I'm hoping to branch out soon, but for now we're here. I'm pretty good at remembering to tilt my screen because there are 2 positions of the screen, top of the board and bottom of the board. If I forget, I will people remind me.
İyidir. Maria Shunovski'yi görmek ister misin?
I'm sorry?
Bir şeyi var. Lecture for subgraphs.
So let me tell you roughly what I'm going
ne kadar takip edebileceğim böyle saatlerde, akşam saatlerinde. Kameram kapalı, merak etme.
Unless you're talking to me.
Böyle anlatıyorum.
So what I plan to do is, first I'll talk about graphographs, then of course. So first we'll start with graphographs, then I'll tell you what they are, and I'll tell you their significance, and I'll tell you theorems that I know about them. And what I want to do is show you the start of the proof of the strong graphograph theorem, because it's an important theorem, and the methods seem to still be, proving new theorems today. And so, and then everybody tells me it's much easier to read after you hear 20-minute introduction to it. So I'll try to do that. Then we'll talk about so in particular strong graphograph theorem. Then we'll talk about recognition algorithms of graphographs. And the recognition algorithm I'm showing you, so there's the original algorithm from 2006, but then there's a newer and simpler one just from last year. So I'm going to show you the one from last year. And it's interesting, the difference between the one from 2006 and the one from last year. So there are 4 steps in both of them, and there's 1 step that we did better last year. So I'm going to show you that step in its new version. So this is going to be from 2020, let's say. And then I want to talk a little bit about the structure of Cloffe graphs.
Record.
And then, so this is sort of a special theorem, because unlike with excluded minors, when you talk about excluded induced subgraphs, there are very few instances when you can really prove a precise structure theorem for a class of graphs. Usually either the theorems are kind of almost trivial or they just don't exist. And this is a very unusual middle ground where it's really non-trivial, but on the other hand, you can still say it, it's still a theorem. And then I'll talk about relatively recent work on something called chi-boundedness. And that's situations when you can get connections between the clique number of a graph and the chromatic number of a graph. So chi of G is at most f of omega of G. And in general, there's no such function, for an infinite family of graphs, but sometimes there is. When a family of graphs has such a function f, this family is called chi-bounded, and there's been some progress on trying to understand which families are chi-bounded. For which families you can bound the chromatic number as a function of the clique number. And so I'll talk about that. And that will probably take 5 lectures. If not, then we'll do some additional conjecture, but 4 lectures, sorry. But I suspect it will take up all our time. Okay, so now let me start. Okay, so first of all, let me remind you what an induced subgraph is. It's a wise thing to do before I start talking about them for a week. So H is an induced subgraph of G if, first of all, the vertex set of H is a subset of the vertex set of G, and secondly, you're not allowed to delete edges. If 2 vertices of H were adjacent in G, they have to remain adjacent in H. And if UV, BH, UV and BH, and UV is an edge of G, then it's if and only if UV is an edge of G. Okay, so let's do an example. If I start with this graph, so let's call this G, then this, if I look at this H, then this is an induced subgraph of that, because to get this from that, you delete this middle vertex, and otherwise, a pair of vertices that was adjacent in G is still adjacent in H. And then if you look, for example, at this graph, this is not an induced subgraph of G. This is not an induced subgraph of G because to get this from that, what I would need to do is delete this edge and delete this edge. But that's not an allowed operation, right? The rule is if you didn't delete either end of the edge, you have to keep the edge. So this is not an induced subgraph. And I'll denote being an induced subgraph by just the most sign. And so sometimes, okay, so and then another thing is, so I define it like this, but really everything is up to isomorphism. So I'll always say, you know, I'd say 5 cycles an induced subgraph of this graph, and what I mean is there's an induced subgraph of this graph which is isomorphic to the 5 cycles. H, say H is an induced subgraph of G if some induced subgraph of G is isomorphic. So this is just kind of abuse of terminology, but it's convenient. And I'll say sometimes I'll say contains, sometimes I'll say free, and like the only containment relation is that of a
sorry.
Question?
Sorry, I forgot to turn off.
All right, so now, so this is right, and so and then this course is about what can you say about graphs that don't contain a certain induced subgraph. Right, some of you might know that there's a developed theory of graphs with forbidden minors. You can describe the structure, you know, for any little graph H, you can describe the structure of all graphs that don't contain H as a minor. And it doesn't work like that for induced subgraphs, but still, you know, the things to say. I'll try to say. Okay, so now let me move on to the graphs. So another thing is I don't know you at all. So I guess at the end of this hour, Dmitry will tell me if this was too fast or too slow and we'll adjust. But if you have strong opinions, maybe you could tell Dmitry. All right, so what's a perfect graph? So G, it's, well, actually, let me do a slightly more gentle introduction. So when you think about graphs, you can think about their chromatic number. That's when you want to color the vertices. And you know, you color the vertices so that adjacent pairs are get different colors. And if the vertices are adjacent, you want them to have different colors, and you want to do it with as few colors as possible. That's a chromatic number. And there's an obvious lower bound on the chromatic number. That's the clique number of G. right? So a clique is a bunch of pairwise adjacent vertices, and the clique number is the size of the biggest clique. Max number of pairwise adjacent vertices. And so obviously it is always true that the chromatic number is at least the clique number, and you could ask, when are they the same? Right? Question for which G of G equals a matrix. And this is a fun question to play with because there are a lot of theorems that you can cast in this language. So, for example, it's true for vector graphs. Right? For vector graphs, chi is 2 and omega is 2. It's true for complements of vector graphs. Right? You know what the complement of the graph is? It's when you reverse all the adjacencies. Probably from the 1930s or something. Then it's true for line graphs of vector graphs. So what's a line graph? What's a line graph? It's when you start with a graph and then you build a new graph whose vertices are the edges of the graph you started with, and two vertices are adjacent. It's the two edges sharing it. Right? So it's like an intersection graph of the edges. So this one is actually this one you probably know. Let's think about this for a minute. So what's the chromatic number if I start with a vector graph H, and then I make G, which is the line graph H. So let's think about G's clique number and G's chromatic number. So clique in G is a bunch of edges in H that pairwise share a vertex, and it's a vector graph, so it's just a star. So clique in G is a star in H, and then the clique number of G is just the max degree of H. G is max degree of H. Now, what about the chromatic number of G? So what does it mean to color G? It means to cover the vertex set of G with stable sets, with sets of vertices with no edges between them. What does it mean in H? It means to cover the edges of G with matchings, right? A stable set in H is a matching in G, and I'm asking how many matchings do you need to cover the edges of H? Well, there's a name for it. That's the chromatic index, so the H chromatic number of H. Chi of G is chi prime of H. And everybody learns somewhere early in their combinatorics studies that in a bipartite graph,
sorry, what's chi prime?
The H chromatic number and the max degree are the same. If H is bipartite, then chi prime of H equals max degree of H. So we proved this theorem. We proved that for line graphs of vector graph, the clique number and the chromatic number are the same, right? Okay, but it's a nice fact, and now we have a more general way to say it. So then it turns out it's true for complements of line graphs of vector graphs. So take a vector graph, take a line graph, take its complement, and that's also true. And that's again, I think they're probably all theorems of Koenig. But it's usually once you're able to translate the statement about chi equals omega to the bipartite graph, you can either prove it or at least it sounds like a familiar theorem. So this is kind of nice. All right, so far, right, we're thinking about situations when chi and omega are the same. Now and so far we got some nice answers to this question. You can also convince yourself that it's true for comparability graphs. It's true for complements of comparability graphs. And there are many nice classes of graphs where it's true. So, but now let me convince you. So far we're trying to come up with arguments to say this is a good question. Now let me convince you this is a bad question, because do the following. Take your favorite graph on at most 99 vertices, and take this joint union with a clique or with a complete graph of size 100. So in this graph, chi and omega are the same, right? It's 100. But, is this a nice graph or is this an ugly graph? I don't know. There's a whole big chunk here that it's your favorite graph, but maybe it's not my favorite graph. So somehow the fact that chi and omega here are the same doesn't really tell me anything about the graph. It only tells me that there's a huge component, which is, that there's a component which is a huge complete graph. So that's not good, right? This means I'm not going to be able to prove nice theorems about graphs where chi and omega are the same. So you need a better question. You need to ask something where the nice answers are still there, but this kind of cheat, you can't do it. And Claude Berge in the early 1960s was able to come up with a definition that did exactly that. He was able to capture this phenomena, which seemed like deep and interesting, but not include this phenomenon. And what he did, he defined perfect graphs, which I'm now going to tell you what they are. So definition, Claude Berge from 1961. He proved that he said G is perfect if the chromatic number of H equals the clique number of H for every H which is an induced subgraph. Right, so he closed it under taking induced subgraphs. He said it's not enough to say in G chi and omega are the same. You need to say it's true for all induced subgraphs. So then what happens with all of our examples? Well, induced subgraphs of biprotect graphs are biprotect. Induced subgraphs of line graphs of biprotect graphs are line graphs of biprotect graphs. So all the nice examples, they don't just have chi equals omega, they're perfect because they're closed under taking induced subgraphs. What about the example I showed you at the end with the big clique? Well, that one I don't know, because in this example, it's not enough that the clique number is 100. You need that in this graph also something interesting happens. So that exactly ruled out this way to cheat and make examples with chi equals omega. Okay, so in this language we can say biprotect graphs, the line graphs, the complements, and the complements of the line graphs of biprotect graphs are all perfect. Okay, so and okay, so let me advertise this notion a little bit more, right? I mean, somehow I explained to you what I think was the motivation for defining this, but how do you know that you define something good? It's when you define it with, from some perspective, from some motivation, and then turns out it has other properties that maybe are not at all clear from your original definition, but if suddenly this is much nicer than a general graph, that means you hit on something interesting. That means you defined something special. So let me tell you about some more special properties of perfect graphs. So first of all, that's the theorem of Wallace. G is perfect if and only if the complement of G is perfect. And again, let me remind you, the complement means you change all the adjacencies. If two vertices are adjacent in G, you make them non-adjacent in complement in that way. So this was actually, Berge conjectured it when he defined perfect graphs. Conjectured Berge, and this is called the weak perfect graph theorem. So this is surprising, right? From the definition, you wouldn't really, I wouldn't really guess it from the definition, but Berge did. So then there's another interesting fact, and that's due to Grochel, Lovas, and Schreiber. They proved that you can compute the clique number in the perfect graph in polynomial time, and even the weighted clique number. So if I put weights on vertices and ask what's the weight of the heaviest clique in a perfect graph, you can do it in polynomial time. Max weight clique can be solved in poly time in perfect graphs. Right, so you probably all know that in the general graph, this is an NP-complete problem. It turns out, complete miracle in perfect graphs, you can do it in polynomial time. And then, of course, if you believe that perfect graphs are, if you believe the first fact that perfect graphs are invariant and taking complements, then you can also do max weight independent set. And you can actually, so you can also compute the chromatic number, because the clique number and the chromatic number are the same. But in fact, you can find find an optimal covering. That's not clear, but you can do it.
May I ask a question?
Yes, just 1 second. Yes, please.
What about the problem that whether a graph is perfect or not?
About what? I'm sorry.
The perfectness of a graph.
Yeah.
So how do you decide it? Do you have algorithm for it?
There is a polynomial time algorithm to test if a graph is perfect. I'm going to talk about it probably tomorrow. Is that good? Okay. All right. So I guess I may as well write it down now. Can test in all the time if the graph is perfect. Okay. So, all right. So there's something interesting going on. I just want to say something about this theorem. So the way they prove this theorem, the way they find max weight clique in a perfect graph, they record it as a semi-definite program, and then they use theorems from combinatorial optimization, methods from combinatorial optimization, such as the ellipsoid method, to solve it. There's an open problem which I love. Can you do this with what's called the combinatorial algorithm? I don't, there's not a formal definition of a combinatorial algorithm. Somebody said to me, it's an algorithm that doesn't use division. And so far, I'm happy with this definition. So can you find max weight of a perfect graph without using division? And what I really mean is, can you understand the structure of perfect graphs enough so that you could use it to find max clique? And as we continue talking about this, maybe I'll give you some more details on what exactly I mean. But that's a lovely, lovely question that I'm very interested in. Can you find max weight clique in a perfect graph just by looking at structure without doing anything as clever as the ellipsoid method? All right, so let's continue thinking about perfect graphs. So maybe I should tell you that when Berge defined perfect graphs, he made two conjectures about it. So conjecture one was called the weak perfect graph conjecture, weak perfect graph conjecture, and that's now a theorem of Lovas, as I already mentioned. It says G is perfect if and only if the complement of G is perfect. And then he made another conjecture that is called the strong perfect graph conjecture. And that's now a theorem by me, Neil Robertson, Paul Seymour, and Robin Thomas. And what it says is G is perfect if and only if G has no C2k plus 1 and no C2k plus 1 complement for k at least 2 as an induced subgraph. So first of all, let me explain to you what this says. So C2k plus 1 is a cycle on 2k plus 1 vertices, right? This is C3, this is C5, this is C7. C2k plus 1 complement is the complement. So this is, and by the way, I always use a dotted H to represent a number. This is C3 complement, C5 complement is itself. So I can do a C7 complement reliably. Right, so this is a graph where consecutive pairs are non-adjacent and non-consecutive pairs are adjacent, and so on and so forth. So what this theorem says is that a graph is perfect if and only if it doesn't contain as induced subgraphs odd cycles and doesn't contain as induced subgraphs complements of odd cycles, but not of length 3. So we're not excluding like k at least 2, k at least 2. So we're not excluding triangles, we're not excluding complements of triangles. We're just excluding things like that. Okay, so at least we understand what the theorem says now. Now let's see. So some of it is plausible. Some of it is very easy to see. So for example, all of these graphs, they're not perfect. An odd cycle is not perfect. What's the clique number of an odd cycle? It's 2. What's the chromatic number of an odd cycle? It's not 2. Right? If you go 1, 2, 1, 2, 1, 2, 1, 2, you'll get stuck with an odd cycle. Make some, let's say, so chi of C2k plus 1 is 3, omega of C2k plus 1 is 2. So that means we already know something. A perfect graph cannot contain an odd cycle as an induced subgraph, right? Because in a perfect graph, for all induced subgraphs, chi and omega are the same. For k equals 1, by the way, this is not true. Right? For k equals 1, omega is 3. But for k at least 2, you can see that in a cycle, the clique number and the chromatic number are different. So a perfect graph does not contain odd cycles as induced subgraphs. What about complements of odd cycles? Well, maybe I won't explain to you, but you can think about it. It's not hard. But it's true that C2 chi of C2k plus 1 complement is k plus 1, and omega of C2k plus 1 complement is k. So again, for k at least 2. So again, you can't, a perfect graph is not contained as induced subgraphs. So what does it mean? Well, that's half of the theorems. We just proved that if G is perfect, then G has no odd cycles and no complements of odd cycles as induced subgraphs. And what Berge conjectured is that these examples that are not hard to think about, they're in fact the only obstructions to perfection. The only reason for a graph not to be perfect is that it contains either one of these obstructions or one of those obstructions. And that's much harder. That's a 150-page proof, which I'm going to tell you something about. So this direction is easy. Write something down. Easy, perfect, implies no C2k plus 1 C 2k plus 1 complement is k at least 2 as induced subgraphs and as directions. Now, if you believe the strong perfect graph theorem, if you believe the strong perfect graph theorem, you should of course believe the weak perfect graph theorem, right? Because the strong perfect graph theorem says there are two kinds of abstractions from perfect graphs, odd cycles and their complements. But more importantly, there are two kinds of abstractions from perfect graphs and their each other's complements. So if you believe this, then of course being perfect is closed under taking complements. But if you don't believe this, then I don't know why you should believe the first theorem. Why you should make the first conjecture. It's I'm a little bit too young. I just missed meeting Bear, but I would really like to know why he made both conjectures. Like, if he didn't quite believe the strong perfect graph conjecture, did he still think the weak perfect graph conjecture might be true just for some other reason? Or did he just want to give people two problems to think about instead of one because maybe the one is too hard? So I don't know. Someday maybe somebody will tell me. All right, so maybe this is a good time to ask people if they have questions. Amazing. Ask people not to write things in the chat, and now nobody wrote anything in the chat. It's remarkable. Almost never happens. Okay, so let me erase this, and then the next thing I want to do is start talking about the proof a little bit.
I actually had a quick question.
Sure.
You said in the definition of in the fixed definition of a perfect graph, when we looked at all the induced subgraphs, you said under that definition, all the nice properties clearly carried over for the complements of the line graphs of bipartite graphs. Mm-hmm. My question is that fact completely obvious without using the weak perfect graph theorem that that any induced subgraph of the complement of the line graph of a bipartite graph is also the complement of the line graph of a bipartite graph?
Yeah, so what you need to do is, so let's do, it's enough to prove it for line graphs, right? And then obviously taking complements preserves induced subgraphs. So an induced subgraph of a line graph of a bipartite graph is the line graph of a subgraph. Okay, let me write this down. I think we better if I write that. So if I have G, which is the line graph of H, and then G prime is an induced subgraph of G, so then I claim there exists H prime, which is a subgraph of H, so that G prime is the line graph of H prime. Because what happened here, you deleted vertices, so in H you delete the corresponding edges, right?
Right.
And so if you deleted some vertices from G, so then delete the same edges from H, and then G prime is a line graph of H prime, and now you take complements.
Right. I think my question was more about the using the complement in the definition without using the weak perfect graph theorem, but I can ask later.
Yeah, maybe ask me later. If you're asking if it's clear that chi equals omega, that's the theorem of Koenig. Nothing is clear.
Okay. Okay. Thank you.
So let's move on to the proof. So Bears made the conjecture in the early 1960s, and it was solved in 2003. If you look at the publication, it's 2006, but that's because it takes Annals of Math 3 years to publish a paper. But people were working on this problem between 1961 and 2003. It's not one of those problems that nobody touched and then there was a solution. And there were two approaches to the proof. One approach was let's try and understand what a minimal counterexample to this conjecture would look like, or what a minimal imperfect subgraph what a minimal imperfect graph looks like. Right, so let me just write something down. So G is minimal imperfect. If G is not perfect, so if let me write more explicitly, if chi of G is different from omega of G, but all induced subgraphs are perfect. But for every H induced subgraph of G is such that H is different from G, chi of H equals omega of G. So in other words, this is a complicated way to say this graph is not perfect, but all its induced subgraphs are. And so another way to say the strong perfect graph conjecture is strong perfect graph theorem is if G is minimal imperfect, then G is C2K plus 1 with K at least 2, or G is the complement of C2K plus 1 with K at least 2. Right? That's just another way to say the strong perfect graph theorem. And so people were trying to understand, to prove theorems about minimal imperfect graphs, to prove to prove enough about them so that you could deduce that they have to look like this or like that. And there are all kinds of theorems about that, but that didn't quite get you all the way to the end. And then there was another approach, which was, let's try to understand the structure of all graphs that don't contain any of this and don't contain any of those. And if I could really describe the structure of all such graphs, then I could prove that they're perfect. All right, so let me give you another definition. G is merge if no induced subgraph of G is C2K plus 1 is K at least 2, or C2K plus 1 complement is K at least 2. And then another way to say the strong perfect graph theorem is Berge is the same as perfect. And we already said that this direction is easy. So the first approach was understand minimal imperfect graphs. The second approach was understand Berge graphs, understand the structure of Berge graphs. And the proof ended up being, I would say, 2/3 of the way to this approach and 1/3 of the way to that approach. So 2 approaches. Understand minimal imperfect graphs. And understand Berge graphs. And so in the proof and then is somewhere in the middle, closer to the bottom line. Right? And what you want to prove is that no Berge graph is minimal imperfect. Right? If you could prove that, you'd be done. So that's why that's what you want to do. You can go in this direction, you can go in that direction, and all you need to prove is that this line and that line are disjoint. Nobody can be both here and there. All right, so let me now tell you kind of a very high description of what the proof ended up being. So I'm going to just write the last thing that I said. So we need to show no Berge graph is imperfect. It's enough to show that. So I'm kind of saying the same thing in different ways, but I'm doing it on purpose just because it's convenient to be able to go between different ways of thinking about it. Like I'm not wasting your time. I want you to be able to think about it in all these ways. Okay, so let me show you a winning triple of theorems. And I'll put theorems in quotation marks because in my winning triple, no member of my winning triple is actually a theorem. So theorem one, every Besch graph is either basic or admits a decomposition. Theorem two, let me finish writing and then I will say something. Theorem two, every Besch graph is perfect.
Sorry, what is a basic graph?
That's why there's no theorems, because I'm not telling you what the basic graph is. And then theorem three, but I'll explain in a minute what it is. If G is minimal perfect, then G does not admit any of the decompositions of theorem one. So suppose I could prove something like this. And I'm allowed to play with what basic is, and I'm allowed to play with what decompositions I'm using, just so that all three of the statements hold. Every Besch graph is either basic or admits a decomposition. Oh, I see. This should say every basic graph. Every basic graph is perfect. So sorry, I fixed something in theorem two. So start again. Suppose I could come up with definitions of basic graphs and definitions of decompositions, so that I could prove this trip. Right? Every Besch graph is either basic or admits a decomposition. Every basic graph is perfect. A minimal imperfect graph does not admit any of the decompositions. Well, then I'm done. Then I've proved the strong perfect graph theorem, right? Because suppose the strong perfect graph theorem is false, then look at the minimal counterexample, minimal undertaking induced subgraphs. So it's a Besch graph, right? We're proving that all Besch graphs are perfect. So it's a Besch graph and it's not perfect. Because it's a Besch graph, it's either basic or it admits a decomposition. But it's not perfect, so it can be basic. But it can be minimal imperfect because it admits a decomposition. So if SPGT is false, there exists G, which is Besch and minimal imperfect. But then by theorem one, G is basic or admits a decomposition. In this case, we get a contradiction to theorem two. In this case, we get a contradiction to theorem three. So this is a nice idea, right? Because it doesn't tell you what you need to prove. You don't need to guess what you need to prove. You just need to prove something that you can fit into this model. And that's also why I'm saying it's kind of in the middle between understanding Besch graphs and understanding minimal imperfect graphs. Theorem one is understanding Besch graphs. Theorem three is understanding minimal imperfect graphs. And then theorem two is what brings them together. Okay, so the only problem is that I haven't told you the theorems yet. I just told you here's something you could try to prove. So let me tell you the theorems now. And again, I'll tell you one set of 3 theorems, but there are others. You don't have to do that. You have some flexibility, right? All right, questions about this? Because this is the base for the next hour of my talk. Have questions about this? It's a good time to ask. All right, so what I need to do next is define basic graphs and define decompositions, right? So basic graphs. And basic graphs you've already seen. These are bipartite, confluent bipartite, line graph of bipartite, complement of line graph of bipartite, and right so far we already proved that they're all perfect. And for a while, and it was, this triple of theorems was conjectured with those 4 basic graphs. Unfortunately, something didn't work. So we need a fifth class of graphs, which are called double split graphs. Now I have a very vivid memory. So I was a graduate student when we proved this theorem. I was telling my friend who is an ergodic theorist about this theorem. I said, we have 5 basic classes. And he said, you can't have an odd number of basic classes for a theorem that's self-complementary. And I was terrified for a minute. But in fact, the reason, and of course he's right, if you're proving something self-complementary, anything you prove should also appear in the complement. Everything should be even. But the thing is, this class is self-complementary. The graph is double split if and only if its complement is double split. So the theorem is okay. Then maybe, well, I'll tell you briefly what these are. But if you don't, if it doesn't sink in your mind, it's not so important. So you know what a split graph is. A split graph is a graph that's the union of the clique and a stable set. That's split. So now double split has nothing to do with split except for the intuition. So in the double split graph, you have a matching, induced matching, right? That's sort of like your stable set. And then you have the complement of the induced matching. So that's a clique, except you deleted some edges from it. And then in a split graph, some pairs are edged. So let's say this is called A1, B1, A2, B2, A2, AK, BK, and those are called C1, B1 up to CM, DM. So then in a split graph, right, between the clique and the stable set, some pairs are edges and some pairs are non-edges. So here I'm going to record it by saying, or to mimic it by saying, so here the rule is between every non-edge here and every edge there, the edges is just an induced 2-edge matching, right? So for every CI, DI, and AJ, BJ, what you have between them is an induced matching. And then somehow, and then there are 2 kinds of induced matching. Maybe C goes to A and D goes to B, or maybe it's the other way around. Maybe C goes to B and A goes to D. So this is called a straight matching. And this is called a twisted matching. It probably should be that way. That's what it's called. So, right, so here I have a clique and a stable set, and every clique vertex to stable set vertex is either an edge or a non-edge. Here I have a complement of a matching and a matching, and between every non-edge here and every edge there, it's either a straight matching or a twisted matching. And again, it's really not very important. It's just some class of graphs which are self-complementary. Okay, so these are the basic graphs. And if for some reason you really want to know, you can read about it in the paper. So now let me tell you the compositions. So there are two decompositions. There are skew partitions. And there are two terms. Okay. So what's a skew partition? The skew partition means V of G is I'm trying to think what's a better way to say it. Let me say it the simple way. A union B union C union D. So disjoint union of 4 non-empty sets. And the rule is everybody in B is adjacent to everybody in C, and there are no edges from A to D. All right. So, so a graph admits a skew partition if you can partition its vertex set into 4 parts, so that B is everybody in B is adjacent to everybody in C. I'll call it B is complete to C, and there are no edges from A to D. I say A is anti-complete to D. So I'll write it down just for terminology. B is complete to C. A is anti-complete to D. Okay, so this is nice. Well, what's nice about it? Well, it's self-complementary, right? If I take complements, what do I get? I get that all the edges between these two are present and none of the edges between those two are present. So G admits a skew partition if and only if G complement exists, it admits a skew partition. And that's nice. That means it somehow belongs to the world of perfect graphs, which is self-complementary. G admits a skew partition. If not, if G complement admits a skew partition. And Vašek-Vatel conjectured that skew partitions are good for theorem 3, that the minimal imperfect graph does not admit a skew partition. So conjecture, it's called skew partition conjecture. Vatel, a minimal imperfect graph does not admit a skew partition. Now, well, is this conjecture true? I mean, we know it's true now because there are no minimal imperfect graphs. I mean, because all minimal imperfect graphs are odd cycles in their complements, and you can check that they don't admit skew partitions. But what about before you prove the strong perfect graph theorem? Is this conjecture true? And if you're going to use skew partitions and say they can't appear in the minimal imperfect graph, then you need to prove this before you prove the strong perfect graph theorem. And we couldn't. But remember, there is flexibility. You can make up decompositions, whatever decompositions you want, as long as you can pad them with basic graphs on the other side. So what you do is, instead of talking about skew partitions, you talk about something called balanced skew partitions. What's a balanced skew partition? It's a skew partition, but there is an additional rule that every time you have two non-adjacent vertices in B of C and a path between them with interior in A or D, such a path is it. And the same in the complement. Every time we have two adjacent vertices in A or D and an antipath, the complement of the path between them with interior in B of C, this antipath is it. And again, if you haven't thought about this ever, it's not so important that you understand exactly what this means, but it's some other self-complementary condition, right? Something about path and antipath going between middle and outside. And so, so instead of using skew partitions, let's promise to only use balanced skew partitions. And then what about this? Well, this now becomes a theorem. So it's now a theorem of us, me, Neil Robertson, Bolsinger, and Robert Thomas, that says, and so it's almost the same. it's a smallest version perfect graph. If G is Berge, not perfect, and with the smallest number of vertices subject to that, subject to all of that, then G does not admit a balanced skew partition. Right, so this is good enough for theorem 3. If you're only going to use balanced skew partitions, and you can prove that a minimal counterexample, so now it's not minimal, it's minimum, but good enough. Counterexample to the strong perfect graph theorem does not admit a balanced skew partition, then that's still a decomposition you can use. It's still in that realm. So that's what we ended up doing. And sort of, it was the conjecture I just raised, Chvátow's conjecture. It was a well-known conjecture. It was called this Chvátow's skew partition conjecture. And, we were very pleased when we solved it, except somehow we solved it in a roundabout way. We solved it by proving the strong perfect graph theorem. There was a practical question attached to it because Gerard Conjals promised $5,000 for the strong perfect graph theorem and $5,000 for the skew partition conjecture. So now what if you prove the skew partition conjecture by proving the strong perfect graph theorem? Do you get $10,000 or $5,000? That's easy math, but it's very important. So pleased to report you get $10,000. All right, so let's continue. So this is skew partitions except balanced skew partitions. And again, let's just sort of run through it again. It's very nice. It's self-complementary. It kind of does exactly what you think it should do in terms of perfect graphs. It's really a lovely, very elegant decomposition. What's a two-join? A two-join means the following. You partition the graph into 6 sets. A1, C1, B1, A2, C2, B2. And then the rule is A1 is complete to A2, B1 is complete to B2, and there are no other edges from top to bottom. So no edges from A1 union C1 union B1 to A2 union C2 union B2, or as I always say from top to bottom, except A1 is complete to A2 and B1 is complete to B2. And that's a two-join. And that's nice. That tells you somehow the graph is broken into 2 parts and communication between them is very limited. If you make a matrix of vertices on top, like the columns are vertices on top, the rows are vertices in the bottom, and then you put 1. If 2 vertices are adjacent, what this matrix looks like is just like this. A1, C1, B1, A2, C2, B2, right? And that's what your matrix looks like. It's a rank 2 matrix. So that's again somehow a nice decomposition. And it was known as the theorem of Conjals and Cunningham that they cannot occur in a minimal counterexample that's Berge. You need to have some non-triviality condition. Like for example, if I have a graph, if I take an edge in a graph, and I look at it, and let's say it's an edge in no triangle, so then the graph looks like this. Well, this does not count as a two-join. It needs to be a little bit non-trivial. And even if this is a path, that still doesn't count as a two-join. So it needs to be a little bit non-trivial. So this rule plus non-triviality. And then it's a theorem that two joins cannot occur in minimal and perfect. and that's the theorem of Korner-Johnson-Kramer. So this is nice, and let me just tell you that. So I'm going to say theorem 1, theorem 2, and theorem 3, and then I'll stop. I know it's 11 o'clock. So the theorem we prove is that every Beres graph is either basic in the top sense, or it admits a balanced Q partition, or it admits a two-join, or it admits a two-join in a complement. Right? Because balanced Q partitions are self-complementary, this is not self-complementary. G admits a two-join, G complement doesn't. And then there are the three theorems that all basic graphs are perfect, and decompositions cannot occur in minimal counterexamples, and you're done. So maybe let me write this down, and that's where I start tomorrow. Theorem 1, if G is Beres, then either G is bipartite, complement bipartite, line graph of bipartite, complement of line graph of bipartite, or a double split graph.
Could you move the camera up, please?
Yes, I'm sorry, thank you. Thank you very much for reminding me. Or G admits it's a balanced Q partition, or G admits a two-join, or G complement. All right, so that's theorem 1. And then theorem 2 is, and those are called basic. Theorem 2 is basic graphs are perfect. And then theorem 3 is if G Beres imperfect with smallest number of vertices subject to that, then G does not admit a balanced Q partition or a two-join, and G complement does not admit. All right, and now, as we already discussed, this is my winning triple, but without the quotation marks. All right, and let me stop here for today. Thank you. If you have questions, you're welcome to stay and ask me. Thank you.
So I actually wanted to ask, so what worked about the balanced Q partition that didn't work about the Q partition?
I mean, nothing. The proof uses balanced at every step.
Yeah, I mean, like, does it have any like nicer properties that like helps the proof? Like...
Oh yeah. So okay. So let me answer your question better. So what happens if your graph admits a balanced Q partition? Like this. Then what you can do is, so it's not exactly true what I'm saying, but it's a little bit. You can squish B. You can replace B by a single vertex that you make adjacent to C. And you can look at this graph, for example. And you can prove, so there are all kinds of edges here, but now I'm just replacing B with one vertex that's complete to C. and has no edges to it. And if the skew partition you started with is balanced, then this graph is still better. Right? I mean, the easiest thing to check is, right, so you need to check that this vertex is not in any odd cycles or complements of odd cycles. Well, one thing that could happen is an odd cycle like this, but it can't because the skew partition is even. So a cycle like this is even, right? And there's some other things. But so with a balanced skew partition, you can do this. You can go to this smaller graph and they say this graph is bearish and it's smaller, and so it's perfect, and all kinds of good things happen. But if your skew partition is not balanced, then you can't start it. All right?
Thank you.
Sure. And yes.
Dr. Chernovsky, do you think there will ever be a simpler or shorter proof of the strong perfect graph theorem?
I don't know. There is already a slightly shorter proof. Paul Simmer and I were able to cut it down from 150 pages to 110, which felt like a great accomplishment. But I really don't. I mean, I'm hoping there might be some proof with, like, I don't know, some algebra or something, where you rewrite the problem in a different language and then use tools from another field. So I don't know if that counts as a shorter proof if you use theory that's already been developed. But I really don't.
Thank you.
I'm also not sure how much people are trying. It's there, it's proved, everybody believes it. If you get a 5-page proof of the strong perfect graph theorem, you'll get a lot of credit. If you get an 80-page proof of the strong perfect graph theorem, I'm not sure, how excited people will be. And some people like me will be excited, but the world in general. So I'm not sure how much effort there is to shorten the proof.
Sir, may I ask a question?
Sure.
So I wanted to know if there are other evidences that, what are the evidences that Birch saw and then made the second strong conjecture? So,
I don't.
Yeah, yes. The examples that you said are, of course, evidences, but I wanted to know if there are more evidence in that.
Yeah, it's very hard to say, right? What made somebody think that a statement is true before they proved it.
Yeah, sure. Sorry
I,
for the question.
If I talked
I
to
know.
him about it, I could tell you something, but I never talked to him, so I don't know.
Yeah, it was not a very well-defined question, so sorry about the question, but thank you for the answer.
All right, maybe enough.
Thank you for the amazing lecture.
Thank you very much.
So,
And see you tomorrow. And tomorrow I'm on at 12:15 my time, right?